What if your network could heal itself in seconds? OSPF isn't just another routing protocol, it's a self-correcting superpower for your network. In this video, I'll reveal how OSPF's Link-State magic detects failures instantly and reroutes traffic faster than any other protocol. Want bulletproof networking? Let's dive in. Introduction to OSPF. The two types of routing protocols are those with distance vectors and those in a link state. When a problem on a route occurs in a network, routing protocols must detect it as quickly as possible and quickly find another path. Only link state protocols enable rapid convergence. We will detail the advantages they have over distance vector protocols. First of all, they are more scalable because they can be extended to larger networks. Then, each router has a complete picture of the topology. This allows them to have all the information on all the routers and links in the network. They are able to choose the best path to all routers in the network. Link state protocols send updates when a topology change occurs, and otherwise it's sent regularly every 30 seconds. They also respond very quickly to different topology changes because they establish neighbor relationships with adjacent routers. That is, when a router falls, its neighbors detect it very quickly and give the information immediately to all the other routers in the network. This allows for very rapid convergence. And the last advantage of this type of protocol is that routers have a common view of the entire network. Each router has complete information about the other routers and the different links in the network, and this also includes the metric on each link. A router that runs a link state routing protocol must first recognize other routers and establish a relationship with its own neighbors, exchanging hello packets to populate their databases. In the example, Router 1 recognizes routers 2 and 4 as neighbors. Then the routers exchange LSA-like messages to enable them to build their databases. An LSA describes a router and the networks that are connected to that router. And all this data is stored in the LSDB, which is the router's topology table. This way, it allows routers to learn the complete network topology. Each router will have the same database of the topology of the same area. We can see the LSAs like books, and the LSDB as a library that contains all the LSAs. Once this database is complete, each router runs the SPF algorithm to calculate the shortest path to each destination, and this data is then placed in the routing table of each router. Here, we can see that to join network A, Router 1 will pass through Router 4. Whenever there is a change in a topology, new LSA-like messages are created and sent throughout the network for all routers to change their LSDB bases. And then the SPF algorithm runs again in the LSDB to check if there are new paths to the destinations. OSPF is therefore a link-state routing protocol. When we say link-state, we should rather think of the state of a router's interface, which includes, for example, IP address, the mask, the network, and so on. The collection of all these states forms the LSDB database. Unlike EIGRP, which is proprietary Cisco, OSPF can be supported by multiple router manufacturers. What makes it very widely used in wide area networks is that it is certainly the most widely used in the world on LANs. It was developed to replace the RIP distance vector protocol. Its main advantages over the latter are its rapid convergence and its ability to expand to larger networks. OSPF uses a two-layer network hierarchy that has two main elements. There's AS and area. An AS is a collection of networks under the same administration, which therefore share the same routing strategy. We can see it as a field, and an area is a grouping of networks. We can see them as subdivisions of the AS. In each SA, an area must be defined. All areas must be physically connected to Area 0. This is called the backbone area. This area consists of several interconnected routers. It is responsible for broadcasting the routing information it receives from one area to the other areas. All OSPF-based routing must have an Area 0. This multi-area design is more efficient as the network is segmented to limit the propagation of LSA messages within an area. This is very useful on large networks. The OSPF protocol uses LSP packets to establish and maintain a neighbor relationship, and also to exchange routing updates. In this table, we see the 5 types of LSP packets, which are used by the OSPF protocol. Type 1 are hello packets. This is what makes it possible to establish and maintain the relationship with other OSPF routers. Type 2 contains an abbreviated list of the sending router's LSDB and is used by receiving routers to compare their local LSDB. As a reminder, the LSDB must be identical on all routers with link states within the same OSPF area. Type 3 are LSR packets, which allow the receiving router to request more information from the database. Type 4 is used to respond to LSR packets and to announce new information. And Type 5 are LSAck packets. When an LSU packet is received, the router sends an LSAck packet to confirm receipt of the LSU packet. It can be seen as an acknowledgement of receipt.